And it's amazing how fast things go from my perspective when we're doing this many lessons in a row. I can't believe by the end of today what we're already going to be doing in terms of this course. But that's the way it is. One thing that I talked a little bit about yesterday, but I'm going to do a particular demo on it today. So, oops, unfreeze that so you can actually see the screen. And and this is going to help us with how we're going to get started in exploring a new form of a polynomial function. Yesterday, the polynomial functions that we were looking at, or in the last lesson, were all in expanded form. I mentioned that briefly, right? But they were all expanded. And you know this from grade 10 specifically. In grade 10, you look at 3 different forms of quadratics. You do expanded form, simplified form, which would be like 3x squared plus 4x minus 9, right? That would be an expanded and simplified form. That one's not very useful. It's universal in mathematics. It's useful for algebra sometimes. It's not very useful for properties of the graph because all you can get is the y-intercept. Then you've got vertex form. When you complete the square, right? And you probably did that in grade 11, but it's been a while, so you might not remember. You go, oh yeah, right, I remember of that, but I don't really remember how to do it. That's okay for now. You don't have to know how to do it just yet. But you complete the square from expanded form. That puts it in vertex form. Very useful because you can graph it. You know the horizontal shift, the vertical shift. You know all the details of the function when it's in vertex form. And then there's factored form, which gives you the X-intercepts, which are a huge deal in mathematics. They're often answers to important questions, like real-life questions. Okay? So you do those 3 forms. So it's the same thing in grade 12. We're going to look at different forms of all the different functions that we look at and try to understand the properties that we can pull out of those forms, how we move it from one form to another, and how we use the different forms to get different properties to graph or to solve problems with that kind of thing, right? So that's what we're looking at moving forward. So before we get to that, I'll remind you, hopefully you can see this clearly. That's a quadratic. There's your familiar quadratic from grade 10. You can see the equation right here. So this is just the standard curve, y equals x squared, or f at x equals 1x squared. Your a value is 1. So here's your a value. And if I drag it, remember that stretches the graph up. So it kind of makes it skinnier. Or I can go down and it makes it wider. It's not growing as fast. And then if I make it negative, it flips it down. We talked about that a fair bit yesterday. We have new terminology for that leading coefficient. Used to call that the a value when it was in vertex form or transformation form. Okay? And again, I can stretch it with a flip or compress it with a flip or whatever, right? So that's moving the a value. This is going to be my, in a grade 10, I think they call it the h value, but now we call it the c value. So this is your horizontal shift. And you can see that that is, whoops, did I just double click on something? That is the number inside the brackets there. Yeah, I did. Inside the brackets there. And when it's minus 3, remember, it moves it to the right 3, or 3.1. And when it's plus 3, or 3.1, it moves it to the left. So it has that opposite effect when it's inside the brackets. Remember this? It's coming back to us a little bit. And then I have a shift up and a shift down. But those are not backwards, because it's not in brackets. So that is what you're familiar with, quadratics. So what I want to show you that's a bit new is how does this work when we change the degree and move it up to degree 3? Now, yesterday we saw how cubic functions, degree 3, can look very different because they can also do things like this, right? In transformation form, they don't do that. This is not super important things that you need to know for a test or whatever. I think it's important that you've seen a little bit about cubic functions before we get into what we're going to do. So you can just sit back and relax and listen, in other words, okay? So when it's in transformation form, like quadratics from grade 10, it's not going to do that. But you can do the same transformations as you do in grade 10, where I can move it back and forth. Okay? And I can move it up and down. But notice how it always has that same form where it comes up, kind of goes flat, and then returns to go up, right? And that's a cubic in transformation form. It won't have those turning points. It won't do any of that interesting stuff. It'll just kind of be boring like this, which is fine, okay? And if you think about it, if the shape of this curve is new to you, it makes sense that it would look like this. Why does a quadratic look the way it looks? Because when I plug 2 into x squared, I square it and get 4. So I go over 2 and I go up 4. But if you plug negative 2 in and square it, you also get positive 4. But with a cubic, when I plug positive 2 in and square it, I go up 8. So you can see that 0.8 there. But if I plug negative 2 in, I get negative 8. Because when I cube a negative, it remains negative. So this kind of looks like a parabola where it comes down and curves, but instead of going back up, it goes back down because cubing things remains negative, right? So the shape does make sense. And if you just think about the relationship of cubing a number, you can see how this, the shape of this graph makes sense. But then if we don't do it in transformation form, we start adding other terms like we saw yesterday, they can get even more interesting, right? Okay, and I can stretch it this way. I can flip it by changing that leading coefficient to a negative, and I can do all the same things that I can do in transformation form as we did with quadratics. And then again, moving on to quartic, and then after degree 4, degree 5, degree 6, degree 7, they all kind of follow the same pattern. You can see that a quartic looks a lot like a parabola, and as I said yesterday, it's got a flatter bottom, and it grows faster because 2 squared is 4. But if I have a quartic, it's 2 to the 4. The exponent is 4. 2 to the 4 is 16. So it's got to grow faster to get up to 16 by the time I've gone over 2, as opposed to a quadratic. So it's similar to a quadratic, but it's growing faster, and it is it's got that flatter bottom, but otherwise it's very similar. And then same thing, I can transform it by doing this or doing this. I can move it to the left and to the right, and I can move it up and down. And in transformation form, again, similar to a parabola, similar to the cubic, it's always going to look like this. It's not going to have all those turning points that we saw in the activity and in the work that we did yesterday, where a quartic can do more interesting things like this. Like it can come down and go up and come down and go up. It can do those kinds of interesting things. But in transformation form, it's not going to. Okay? Does that make sense? Okay? All right, good. So we're going to get into the first example here. So what we're looking at today is factored form of a polynomial. This is not transformation form. That was a quick aside talking about that. You're going to see why, hopefully, in a moment, why I wanted to cover that first. We're looking at factored form of a polynomial function. So these are the same kinds of functions we saw yesterday. Yesterday, they were all in expanded form. In factored form, we're going to be able to, again, sort of tease more properties and more details of the graph out of the equation. So it's going to be really useful. So in order to do that, we're going to do 4 things for each of the functions that we see on the page. We're going to sketch a graph of the function, sort of thinking about the transformations. We're going to state the x-intercept, state the degree, and describe the behavior. The description of the behavior is not something that you would be familiar with yet, so that's going to be some new learning that I'm going to share, and it's very specific. The way you would describe it, it is sort of prescripted, like you have to say it the specific way. You don't just describe it yourself. We use specific words, okay? Okay, so what's this first one? Now, this is hard. I know this is tricky because, again, you haven't been doing this for a while. So when I ask about these functions, a lot of people are like, well, I'm not really sure specifically what information he's looking for. Like, what does he mean, what kind of function that is? But usually somebody in the room can share what kind of function it is. What's this first one? Y equals x plus 1. Who knows? Okay, one person. Anybody else think they have a guess? Think you have a guess? Zamzam, what do you think? It's linear. So that's the word that I'm looking for there, right? It's degree 1. when we're talking about polynomials, that's often one of the first things we want to notice is what's the degree, and so what type of function are we looking at here? This is linear. Linear in grade 9, we don't usually include the brackets like that. So this would just be y equals x plus 1. And y equals mx plus b means it has a slope of 1 and a y-intercept of 1. But you could do linear functions in transformation form. And this would be a shift to the left, because you're adding one, it'd be a shift to the left by 1. You could do that. Don't worry, it's not something we're really going to do. Okay, so I'm going to graph this. I'm going to use my ruler. If you don't have a ruler handy, you can probably get away without it, but a ruler is something you're going to want to have throughout the course. And there you go, and I'm going to label the y-intercept just because that's a good thing. And the x-intercept is something that that was one of the questions, one of the requirements, but basically when we're sketching, we always label the intercepts as long as we know them. And what is that the x-intercept going to be? Anybody know? Emma? Not 1 though, because look at it carefully. Which flavor of 1? Yeah, negative. Very good. -1. Okay, so it's -1. That's correct. So we sketched it. B, the x-intercept is -1. What's the degree? Well, linear, so that's question C. 1. Now, when it says describe the behavior, I'm going to put this in quotations just to show that it is worded carefully. I'm not just describing this randomly. You don't have to put, I wouldn't expect you to always put it in quotation marks. That's not a thing where you always put quotation marks around these descriptions. But when I give a term that's a specific term, sometimes I put it in quotation marks to sort of communicate that to you. Okay, so we call this straight pass-through. Now, we often drop the straight part of that when we're describing it. And in fact, generally speaking, if you are going to describe this, it's not often a question that we would ask on a test to describe it in words, and you would write out the word straight pass-through. But sometimes we do sort of describe it just informally as we're doing our work. And so I would usually just do that, just PT for pass-through. So we kind of drop the straight part, but it's a pass-through. So far, so good? Okay. Next one is, what type of function? Like, we have to graph this thing. We have to know what kind of a function is in order to graph it. My guess is almost everybody in here knows what it is. So from grade 10, it's a parabola, right? Yeah, a couple of you are raising your hands now, but it's a parabola. Do we know that? Okay. So, and it's in transformation form. It doesn't have a lot of transformations. So what is the transformation? You don't have to actually answer this, but I want you to think about it. What is the transformation? And now you can start to see why I wanted to do that visual demo ahead of time to sort of tap into your understanding and your knowledge of that from years ago. So it's a horizontal shift, right? Which direction? To the right by 2. So the vertex of this is going to be on the x-axis because it doesn't shift up or down. Okay, and I'm just going to kind of casually draw I'm not worried about the y scale, so whether the y-intercept is on there or not, that's not necessary for this. So what's the x-intercept? Positive 2? Okay. So I'm going to label it and answer the question. The degree of a quadratic is 2. We talked about that a fair bit yesterday. Now we're going to come back to this later and really hammer this out and talk about it. But yesterday when we looked at degree, we talked about the term with the highest degree because it was in expanded form. When it's not in expanded form, how do you know what the degree would be? So this is something we're going to have to practice where it's almost like without actually expanding, I imagine what it would be like to expand. So I imagine what would happen if I did x minus 2 squared. Now, because it's only x minus 2 squared, I can actually do that fairly easily. I can actually just expand it in my head without any steps, right? And it would be x squared minus 4x plus 4. And I can see that the highest degree term would be 2. So this is something that you're going to have to get used to doing, is looking at something in factored form and imagining what would happen if you expanded it. But we're going to come back to that and practice it even more carefully. So we'll move on for now. And for question D, where it says describe the behavior of the graph at the x-intercept, we call this a turning point. That's words that we already know. And maybe a little bit confusing compared to the first one, because the first one was PT, this one's TP. Coincidence. And now we notice the difference between this one and the first one is this one does not pass through. It turns at the x-intercept and stays above the x-axis in this case. Whereas the first one passed through the x-axis, right? So that's why we called it a pass-through, because it actually passed through, compared to this one that doesn't, it turns. Okay, got that? All right, let's move on. Now this one, what type of graph is this going to be? So again, this is why we just looked at that demo, is because before that, you wouldn't have known how to draw this graph. Okay, but it's a cubic, and it's also in transformation form. So it's got a shift to the right by 4, and it's going to have that familiar cubic look. Not that familiar to you, but if you practiced it, it would be, where it comes up, looks kind of like a parabola from one side, but instead of turning back down, it flips and turns up. One half of it goes up, one half of it goes down. Otherwise, the way that it turns and behaves is similar to a parabola. So this has a shift to the right 4, which means normally, don't write this down, normally it would do this at the origin. So instead we're going to shift that over 4. And watch when I'm drawing this. It's almost like I draw a parabola on one side going down, and then instead of drawing it down on the other side, I draw it up. Some people have a really hard time drawing these for whatever reason. So if you draw the this cubic function and that little shape, because you're going to be doing it a fair bit, if you draw it really wrong, you could lose marks on a test for that. Like if you do, like people do, I don't even know if I could try, or they do things like this and they like that or something, and that's not that's not the same thing, because that's crossing the x-axis 3 times. So try to remember it comes in from one side and then goes out on the other side the other direction, and draw it in 2 parts like that, and that might help. Or practice. And if you think maybe yours doesn't look right, again, take a picture, email it to me, ask, and I'll tell you like, yeah, no, that's not what they look like. You got to get on the ball and fix that and do a better job. So be careful of that. Okay. Okay, so questions. X-intercept is? Well, it was a shift to the right 4, so it's 4, right? Degree? So again, I can imagine expanding this. It'd be x minus 4 times x minus 4 times x minus 4, right? I'd be multiplying that bracket, x minus 4, times itself 3 times. That's what an exponent means. So my leading term would be x times x times x, which would be x cubed. So this is cubic. We already kind of know that. Degree 3. How do we describe this one? We call it a cubic twist pass through. But we shorten that to just a cubic twist. So when we say pass through, we mean straight pass through. When we say cubic twist, we mean a cubic twist pass through. Because again, it does pass through the x-axis, right? It goes through the x-intercept to the other side, but it does it with a twist. Compared to the linear, that goes straight through. And as you can probably imagine, we can shorten that just to CT. Often you are just going to be making these notes for yourself to remind you that that one should be a cubic twist. And so you can just CT and you'll remember. And again, for those of you taking calculus, there's a huge part of calculus where you will have to describe the behavior this way. We do it in a big table, a big chart, and you'll use these short forms. So even if you could get away with it in this course with not writing it down, you will, if you take calculus, you will need those. We good so far? Any questions? All right, one more quick one. So this is degree 4. Again, this looks like a parabola, but with a flatter bottom, okay? And this is transformation form again, so it's got a shift to the right 5, so I'm going to bring it way over here, and otherwise no other transformations. When you're drawing these, you don't have to go out of your way to make it look like it's degree 4 quartic and has a flatter bottom. Like I'm not going to say, ooh, yours looks more like a parabola than it does like a, I wouldn't, or I never have at least, worried about that. So, you know, for this one, I am going to kind of draw it a little bit more flat maybe, but generally speaking, whether it's degree 2 or degree 4, for what we're doing right now, you know, it's a turning point. It turns at that location. It would be a bit flatter if you graphed this with technology and the technology was giving you a perfect graph of it. It would look a bit flatter. But for our sketches, which is what we're doing right now, we're not doing accurate graphing. We're going to be doing some sketching. We're not going to be too picky about that. So the x-intercept is 5 because it had a shift over 5. I'm going to label that x-intercept as well. The degree is 4. And again, we would call this a turning point. We would not call it a degree 4 turning point or a flat turning point. We don't describe it any way different from we would degree 2. We get that? So, now this says, using the information above, can we attempt to graph the following function? So notice this has 3 of the same brackets out of the 4 that we did above, so we dropped the last one. But x plus 1, x minus 2 squared, and x minus 4 cubed. Those are the first 3 examples that we did. Does everybody see that okay? See how it matches? So what is this going to look like? Now, I'm going to help us out with the first one, but when you actually start to do this, you also have to think about the degree of the entire function and the leading coefficient to understand the end behavior. So I'm going to help us out with that part because we're going to come back to it in a minute. this function turns out it would be degree 6, which is even, which means what about the end behavior? Even functions, their end behavior is either both up or both down, right? So I know that because this is degree 6, it's either both up or both down. That's something we learned yesterday. And then this one will have a positive leading coefficient, so that means both up. So that means this is an x-intercept at -1, just like it was up here. That is a straight pass-through. The next one is an x-intercept at +2, just like it was up there. That's a turning point. The next one is an x-intercept at +4. That will be a cubic twist. So again, this is new information. You might have guessed this if I had challenged you to try to figure it out yourself. You might not have, that's fine. But turns out that when I graph these separately, or I put them all into one big function together, that they have the same behavior as they do when they're graphed separately. So watch this. So because remember my end behavior is both up. So I'm going to start up and I'm going to go straight through, and then I'm going to do a turning point, and then I'm going to do a cubic twist. And you might not do that all in one shot. You might do that in little bits at a time. That was actually lucky that I didn't mess it up graphing it all together in one shot. But see how that works? So I've got an x-intercept at -1. That was a straight pass-through. I've got an x-intercept at +2. That was a turning point. And an x-intercept at +4. That was a cubic twist. Now, that's starting to look like the kinds of graphs we were looking at yesterday, doesn't it? Where it's got all kinds of turning points and twists and funky things going on, and it's not just those basic ones in transformation form like that. It's got more interesting details. And this is the kind of thing that we're working on for the next couple of lessons. So right there, the fact that I can look at this is in factored form, right? I could expand that into expanded form, but this is factored form. And from factored form, I can get the x-intercepts, and I can understand what the graph looks like at the x-intercepts. And I can use that information, and we're going to do a little bit more than just that, but I can use that information to get a relatively good sketch. This is not an accurate graph, it's a sketch, but a sketch of the function. And that's kind of what today is all about. Now, you'll notice that my sketch is a little out of scale because my -1 and my +2 to me look like about the same distance from the y-axis. Do you agree? So if I was doing this for my homework solutions that I post online or for a test, I would try to be a bit more careful to make it look a little bit more to scale, but it doesn't have to be to scale. But you do want it to be kind of to scale. If you have one x-intercept that's 10 and one that's a half, like you want to kind of reasonably well have them distanced to scale, but not to an exact scale. We're not getting out graph paper, we're not pulling out a ruler and making tick marks or anything like that. But generally, I would try to make the -1 in a little bit further than the 2, and that'd be good enough. All right, let's keep going. Any questions? No? Okay, on the back of this sheet, here's a quick summary. So I've already kind of talked about all this, but I am going to talk about a couple of things. First of all, there's a word we use. Oh, it's not even in there. That's okay. There's a word we use to talk about this behavior, and it's called the order of the x-intercept. It's the same thing as saying the degree of a particular x-intercept, but we use the word order. So some of the questions are going to say like, what is the order of the x-intercept? Okay, and it just means the degree. So if I went back here, the order of this one is 1, of this one is 2, and of this one is 3. The degree of the entire function, as I said, was 6. But each individual x-intercept also has a degree, and we call that the order. And so this is summarizing that x minus a, so this has a degree of 1, or an exponent of 1. That has a pass-through, x-intercept at a. X minus a squared is a vertex or turning point, x-intercept. Cubed is a cubic twist, and then after that, if it's even, we still call it a turning point. If it's odd, we still call it a cubic twist. Because we'll see a little bit of degree 4, 5, probably not beyond that, but you could. It would be the same kind of idea. Okay, so that's called the order. I'm going to write that down. And you can see right here in example 2, it says consider the order of the factors of each polynomial. And we're going to think about any other information, and we're going to match it to the graph. Okay? Everybody with me? Now, in the homework, there's some of this. In the learning goal, tied to this lesson, I think there's a question that has 5, 6, or maybe even more graphs that you're matching. Some of them you can match really easily. You can be like, well, there's only one degree 3 polynomial, so it's got to be number 5, right? Like you could match it with one property. Or you might say, well, there's only one that opens down, so it's got to be this one. And that's fine. If you had those questions on a test, generally speaking, when I ask that question on a test, I just say match the graphs. But for practice, you may challenge yourself to list out all of the information. The order of all the x-intercepts, their order, the degree, the leading coefficient. Like you might list all the information that you can. Just for practice, that would be up to you. And on a test, it could be asked, state the following for each of the functions, then match it to the graph. So you would have to follow those instructions, which could be things like state all the x-intercepts, their order, and blah, 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 right? So in that case, this doesn't say that. It says consider it and consider any other information. I want to get through this fairly quickly, so we're not going to go through it in a ton of detail. But for your homework, I don't know, you might, depending on how busy you are. Okay, so this first one, what are the x-intercepts? And what is each of their order? I'm going to just kind of do it in a little informal chart here. So this is in factored form. Factored form means everything is in brackets. There's not like a +7 at the end. That does not count as factored form. Okay? So I look in the brackets at the numbers. 2 brackets means 2 x-intercepts. And as we saw lots in grade 10 and in grade 11 when we do transformations, when it's in a bracket, it has the opposite effect that you might expect. And so adding 2 is actually shifting left 2. So this is an x-intercept of -2. And its order is the degree of that x-intercept, which is 2. X minus 3 means an x-intercept of 3. That one has no exponent, so the exponent is obviously 1. So it has a degree of 1 or an order of 1. So this is a turning point, and this is a straight pass-through. If there were more of these, we only have 3, and they don't have a lot of variety between them. If there were more of these, I might also have to think, well, what's the degree? So the degree of this one is 3. What's the leading coefficient? Well, it's going to be positive. We're going to come back to that and talk about it more in a moment. And I look at all 3 graphs and I say, which one of these has a pass-through at 3 and a turning point at -2 and is also degree 3 and also has a positive leading coefficient? How many people think they know which one it is? Okay, good. Oh, good. Did you guess 3? Okay. Turning point at -2. Pass through, straight pass through at +3. What about B? So I'm going to give you a hint. This one has 3 x-intercepts. One of them looks a little different, and we haven't quite seen that type before. And this is what I mean. Once I realize that this one has 3 x-intercepts and I look at those 3 graphs, well, I can figure out which one it is. I don't even have to look at what kind of intercepts they are. Only one of these graphs has 3 x-intercepts. So I already know which one it is. But the point is the learning, not to just get the answer. So the point is to dig a bit deeper and look for more properties that are matching. What are the 3? Well, this one is an x-intercept at -3. I'm going to do them in order from left to right. You don't have to do that. Okay? Its order is 4. So that's turning point. What's the next x-intercept? Anybody know? Una? 0. Where does that come from? The x out in front, right? Because that's like an x plus 0, which is just x. So I have an x-intercept of 0. That has order 1, so it's a pass-through. And I have an x-intercept at +1, which is order 3. That one right there, which is a cubic twist. So this one's got a little bit of everything. Now, what's actually really cool when you have it written out like this is if you add the orders together, that's your degree. So my orders are 4 and 1 and 3. Add those together, I get 8. This would be degree 8 polynomial. And that's even. So both up, both down. This has a positive leading coefficient, so both up. Right? So I can very quickly get a lot of information, a lot of properties of this function just by looking at the equation. Remember yesterday when I was introducing this course and I said that's what this is all about. Look at the equation. What does it tell you about the graph? Look at the graph. What does it tell you about the equation? Right? Going all directions. So we're getting right into it already, where I can just look at the equation and get all these important properties. Any questions so far? Some of you might be a little bit still unsure of why the x is an x-intercept of 0, but we'll see that again and come back to it. So I'm not going to dwell on it right now. So it's going to be number 1. Number 1 has a turning point at -3, a pass-through at 0 and a cubic twist at 1. So it's graph 1. So then by process of elimination, again, we already know that the last graph is graph 2. But I still want to talk about it because that's not the point of this example or this exercise. The point is learning. Questions yet? Say again? Yeah, for C, what about it? Like, before you say that, because I think I know what you're going to say. Something different about C from the first two examples? What is it? Huh? It's not factored, exactly right. Not in factored form. There's your expanded form from yesterday. Expanded form is not the same as factored form. In other courses like grade 10 or grade 11 courses, people start to think, oh, so the X-intercepts are 8 and 16 or something like that. You start making up other things. Oh gosh, no, right? So in expanded form, we just don't know the same information about the graph. So what do we have to do? You got to factor it. But this is cubic. We don't know how to factor cubic degree 3 polynomials. You only know how to factor quadratics that you learned to do in grade 10. So what are we going to do? Now this one is special because it has a common factor of x. So we actually are going to be able to factor this one just because we're lucky. If only we could learn how to factor higher degree polynomials. Oh, wait, right. We're doing that in this unit in this course. So that's coming. That's a major part of this unit is learning how to factor higher degree polynomials. If you are rusty at factoring, you better get on the ball and practice. And I posted a bunch of review for that. And if you didn't do it, that's fine. But over the weekend, maybe you go and do it. Okay? Because factoring simple trinomial like that, or even complex trinomials, that has got to be easy business for us at this point. If you struggle with factoring those, you're going to have a hard time with all the extra stuff that we're going to do. You want to be able to do those without thinking, just fast, fast, fast. Every little detail that on a test that you have to think about that maybe other people don't, that slows you down and that causes you to run out of time on a test. How do you avoid that? Practice. The more you practice, the more natural you get. It just becomes automatic. Now that's in factored form. Again, I've got an x-intercept of -4 and 0, and the order is 2, so that's a turning point, and 1, so that's a pass-through. And again, we already know that it is graph 2, but again, now we know even more that it's graph 2, because we can see that it has a turning point at -4 and a pass-through at 0. Whoops, 2. How's that? Yeah. If you ever miss part of the note, and if I move too fast, because sometimes we do have to move on, just grab it, just leave it blank, make yourself a little note that you're missing something, grab it from the classroom, right? Or at the end of the lesson, say, can you put that back or whatever? Because sometimes we have to move on. We got to squeeze things in. Got to move fast. All right, example 3. This one's quick, and then we're going to move on to the final page, which has some really good stuff on it. Well, it's all good stuff, but you know what I mean. This one says, sketch a possible graph of a polynomial function that satisfies the following conditions. often when it says that, what it means is there are lots of properties or details that we don't know. So you got to make them up. And your graph might look different from the person sitting beside you. Okay? And that's okay. As long as it satisfies the conditions, you'd be fine with it. So it says degree 4. Negative leading coefficient. 2 zeros, that means 2 x-intercepts. 3 turning points. So let's talk about each one of these things sort of on its own. Degree 4 is even. So that tells us end behavior is both up or both down. Okay? Like that's just what we know. And some people will say, well, how do you know that? Because that's the way that it is. That's just a fact. And if you don't know that yet, that's okay. Sometimes it takes some getting used to, but eventually you need to just know that. You need to just know any even degree polynomial function will have end behavior such that both ends are pointing up or both ends are pointing down. Okay? Negative leading coefficient means what? Both down. So with those two details, sometimes what I do is I pencil in the end behaviors, and my graph is not necessarily going to match up with those. I might erase them at the end or something, but I'm just marking it on my graph to remind myself that's what the end behavior has to be. Okay? And then next we have 2 zeros, so 2 x-intercepts and 3 turning points. So don't draw this yet. I'm going to draw a few different ones, some that are going to be wrong and a couple that are going to be right. And then whichever one you choose to draw in the end can be up to you. What if I did this? That could be a degree 4. They can look like that. I mean, that's pretty sloppy, but they can look like that. That's what we saw when we did the transformations. It's got 2 x-intercepts, 2 zeros. What is it missing? The turning points. It was supposed to have 3 turning points, so that's not good enough. So there's a few different ways I could draw this. I could go like this. 3 turning points. 1, 2, 3. 2 x-intercepts. Right? I could go like this. 2 x-intercepts. 3 turning points. Do you agree? I could get really fancy and I could go like this. 1. Whoops. Except that was wrong. 1, 2 turning points, 2 x-intercepts, 3 turning points. Bam, like that. I think those are probably the only ways that you can do it. I mean, you could make them look a little bit different, obviously, but those are kind of different ways that you could have x-intercepts. But any of those 3 graphs would satisfy these conditions. So this is what I mean. Yours may not look exactly like someone else's, as long as it satisfies the conditions. So I'm going to do this one. 2 x-intercepts, 3 turning points, 1, 2, 3, and we're good. So sometimes in the practice, like one of the practice questions I think asks you to do that kind of thing. So you just have to satisfy the conditions. It's not going to be as accurate. You don't know where the x-intercepts are. You don't know exactly where the turning points are. That doesn't matter. All right. Final example. And this one's got a lot of steps to it. But there's something really important that we need to learn how to do. That's part of this process. And then the other parts are hopefully going to be a little bit faster. We'll kind of get through them a bit more quickly. Ready to go? So for each of the following, there's 2 graphs. We are going to partially expand the polynomial. Now this is something that you're forced to do because the question says to do it. And in the homework, I believe it says the same thing. On the test, it might not say that. So you can do it on paper, which I don't know why you wouldn't. Like this is how I'm teaching you to do it. So this is the strategy. But if you can do it in your head without writing it down, I mean, it's not a prescripted requirement that you always show this step. Does that make sense? Okay? Unless the question says that. Maybe on the test this year it will say that, in which case, of course, you have to. But when we're sketching in factored form, doing this either in your head or on paper is a requirement. Something you have to do correctly, be able to do correctly, and at some point do it to figure stuff out. So let's get started on that. Whoops. Y equals. So I'm going to partially expand this. What does that mean? That means I'm going to imagine, and I think this is new. This is a new type of thinking and a new kind of skill. So you got to be open-minded here and bear with me and sort of try to follow the steps. And when you're doing the practice, go back and look at the lesson. Maybe even watch this part of the video where I describe how to do this and practice doing it, because this is a new skill. I have to imagine if I were to expand this whole thing. If I were to actually expand the whole thing, it'd be negative 3 times x minus 1 times x minus 1 times x minus 1. I'd have 3 of those brackets times x plus 2. I would have 4 binomials that I would be expanding. That's a lot of work, isn't it? You'd have to this times this and this times this and this times this. And like, it would be a lot. It would take a long time. Look at the next one. X times 2 of those times 3 of those times 1 of those. Holy cow. Like, you don't actually want to expand this. It would take you 10 minutes just to do that part. So we're not going to actually expand it. We're going to imagine expanding it. And I can imagine if I expanded this, again, it'd be x minus 1 times x minus 1. Don't write this down, times x minus 1. Just watch. And I would get x times x times x as my first term. And when I expanded this, I would get x cubed. Can you follow that? Does that make sense? And this one is just x. So my first term would be negative 3 times x cubed times x when I expanded all the way through. So it would be negative 3x to the 4. Do you understand that? I mean, if you don't, this is what I'm saying. You have to go back and think about it more and figure that part out. We're going to do it again with a harder question, quite a much harder question, actually. We're going to do it again, but this is something you need to be able to do. And then I'm going to skip everything else because I don't care about the middle terms. In fact, I only care about the first term and the last term, which is great because those are the easy ones. Question?
Are we like supposed to or allowed to like with dot dot dot? Or, like if
For this, yeah, that's what it means, partially expand.
Oh, okay.
I don't want you to actually expand it. That's not something we ever do in this course, hardly ever do in this course, would be expand a degree 4 polynomial like that. Like it's just a waste of time. You could do it. There are times where you might have to expand cubic a little bit, or we expand quadratics a fair bit, but otherwise, it's just not something we do. Okay, and then I'm looking at the last term. So if I was cubing this bracket, I'd be cubing negative 1. I'd get a positive 2 from this. And I would have the negative 3 from out front. So again, I'm only taking the constant from each factor or each bracket, applying the exponent, and actually multiplying it out. So is that positive 6? Negative 3. So negative 1 cubed is negative 1. So it's negative 3 times negative 1, which is 3. 3 times 2 is 6. So what we do is we do dot, dot, dot plus 6. So again, to answer your question, are you allowed to do that? Yes, exactly. That's what you're supposed to do. That is the partially expanded version of that polynomial. And yesterday when we did that activity, you saw degree 4 polynomials that were fully expanded. They had all of the terms on the inside. But we don't care what those terms are. They're not going to help us. Why is the first term important? Gives us the degree, gives us the leading coefficient, which will give us the end behavior. Why is the last term important? Anybody know? It's the y-intercept. The last term in expanded form is the y-intercept. So therefore, your y-intercept is 6. Okay, now I want to get through this next part quickly. Degree is 4. Leading coefficient A is -3. If there's anybody wondering, the 3 part really doesn't matter. It's the fact that it's negative, or it's the fact that it's positive or negative. That's all we actually care about. We don't care that it's got like a vertical stretch by a factor of oh gosh, no, we don't. That's not how we graph these things, right? D. Now this is a little bit weird. D and E are a little bit weird for this question because we know how many X-intercepts this polynomial has. What these questions mean, this is just for practice, what these questions mean is for a degree 4, how many could it have? That's what this question means. So if you remember from yesterday, degree 4 could have 0, right? If it opens up and it's all above the x-axis, or if it opens down and it's all below. It could have 1, it could have 2, it could have 3, or it could have 4. Degree 4 can have up to 4. And E, again, the possible numbers of turning points, well, even degree 4 has to have at least one turning point. It can't have 0 because of the way the end behavior works and just because of how they are. And again, it can't have 2 because what would 2 look like? Well, there's 1, 2. Well, that's not degree 4. So if it turns twice, it's going to have to turn again in order to be degree 4. So it could have 1 or 3, but that's it. End behavior. End behavior looks like this. As x goes to -infinity, what does y do? And then as x goes to positive infinity, what does y do? So end behavior is always filling in those blanks. And what is the end behavior? Okay, I want you to look up, I want you to watch. And some of you, I think you probably are getting this and you know it, but some of us are still questioning, how do I know what the end behavior is? Right there, folks. You have to look at the degree and the leading coefficient. That's how you get the end behavior. The degree is 4, so it's both up or both down. The leading coefficient is negative, so it's both down. So -infinity in both cases. G is determine the x-intercepts and the behavior, and their order. So I go back up to factored form here. I hope I'm not going too fast. I go back up to factored form. There's 2 factors. The -3 out front is not a factor. It doesn't count. You have to have an x in it. So I've got +1 and -2. +1 has order 3. -2 has order 1. I usually do them in order from left to right because it's a good habit for when we start doing some bigger sketches later on. I think it helps you speed up your process of some of the big sketches that we do. Just being in the habit of doing things left to right, but not everybody feels that way, so that's fine. It's up to you. So this is a straight pass through, and this is a cubic twist. And now I'm going to take all of that information, put it all together, and sketch this. Ready? Like, you might want to just watch me do it the first time, I don't know. Or you might want to have a go at it yourself. If you're a visual person, you're getting this, you could have a go, that's fine. So again, I could pencil in my end behaviors. The nice thing about the sketching is we have so much information, it all has to match. If anything doesn't match, you're not going to be able to draw the graph. You're going to force it and something's going to feel weird. And if that happens, you should stop and go, wait a minute, what's going on here? So for example, if I had done the y-intercept wrong and I thought it was negative, I would go like this. I have a straight pass through at -2. Wait a minute, my y-intercept is negative. So I'm going to go like this and go like this and then do my cubic twist. But how do I know this is wrong? You've got two x-intercepts that didn't exist in the equation. So I got to go back, realize that my y-intercept is positive. So I go like this. Wait a minute, I'm getting this backwards, aren't I? Yeah, okay. I want to go like this, and then a cubic twist at +1. So that was at -2. Cubic twist, which was a straight pass through. Cubic twist at +1, and I label my y-intercept. When you do a sketch, you're always required to label all the information you know, which it includes the x-intercepts and the y-intercept in this case. And there's your sketch. Any questions? It's been a long lesson again. They're not all going to be this long, don't worry. We've got one more example to do. All right, here we go. So again, the first one was by partially expanding. Now this one's harder to partially expand because it's got some quirks to it. So the best thing you can do is look at each bracket individually and figure out what's happening in that bracket and then put them all together. So you'll notice I'll write it above the brackets and then I'll put it together in the partially expanded form. So this is just x. This is -x. What is this? Well, it's -2x all cubed, which is -8x cubed. So I have to know that that's negative. In that it's 8, that 2 cubed is 8. But if I got that negative part wrong somehow, that's going to really drastically impact my sketch. And this one is just x. Well, that one should be squared, sorry. I missed that. Did you catch that? Anybody? Or you're just following me? So I missed the squared. So I'm coming back, squared. What happens when you square -x? It's going to be positive. So again, that's really important. If you made that mistake, your whole graph is going to be wrong. In fact, you're not even going to be able to really graph it with the y-intercept and stuff. Things are not going to work. So I've got x times x squared. That's x cubed. Times -8x cubed. That's -8x to the 6 times x is -8x to the 7. So this is a degree 7 polynomial function. Okay, now careful. Put your pencil down and watch. You really need to pay attention to this. I know it's been a long time and you're probably kind of getting tired and losing your focus, but you got to watch this. So I've got positive 1 squared. I've got negative 3 cubed. And I've got negative 5. So that is 1 times negative 27 times negative 5. So on my calculator, if I do negative 27 times 5, I get 135. Does that make sense? But this one's special because it's got an x. So that is actually plus 135x. And this one has a y-intercept of 0. So I can see people trying to do the y-intercept and doing this work and thinking it's plus 135, but it's not because of the x out front. So you don't have to show me that, but I show it to remind you to be careful when there's an x out front that it's actually plus 0. So therefore, this has a y-intercept of 0. We're going to notice later that it has an x-intercept of 0. If you have an x-intercept of 0, you better bet you have a y-intercept of 0. Try drawing a function that has an x-intercept of 0 and not a y-intercept of 0. You can't do it. You would draw something that's not a function. So you would start to get yourself confused, and if you're not confident and you're not practiced, you'd start to mess up and you'd give up or quit or whatever, right? You ready to move on? I know it's a lot. No? I know that's a lot. So when you're doing the partially expanded version, you're only looking at the first term and the last term in each bracket. You have to apply the exponents. You have to carefully look at the positives and negatives. And this is a special case where when I do this thing over here, it doesn't actually give me the y-intercept. So just be careful of that. The degree is 7. The leading coefficient is negative 8. Possible number of x-intercepts. Again, we actually know how many x-intercepts this have, but just in general, a degree 7 has to have 1. Can't have 0. And it can have up to 7. So you could just go like up to 7. On a test, if you were asked that, that'd be fine. As for turning points, that's not fine. Odd degree functions can have 0 turning points. They can have up to 6. But it's not all of the values between. It can have 0, 2, 4, or 6. Okay, so be careful of that. F. Again, I look back at the degree and the sign of the leading coefficient. The degree is 7. So look, they're opposites. They're either this way or this way. One up, one down, right? And which one is it? Because it's negative, it's up on that side and down on that side. So as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. One more kind of tricky part of this question. Okay, again, I want you to put your pencil down and watch. For some of these, it's easy. This is an x-intercept of 0. This is an x-intercept of 5. Change the sign in the bracket. There's your x-intercept, right? That's not an x-intercept of -1. If I flip that sign from +1 to -1, that's what we always did every other time. That doesn't work. Why? Because of the negative out front of the x. So if you're good at mental math and patterns and understanding these things, and you can do this in your head, fine. If you can't do this in your head, what you need to do for an x-intercept, you're always setting the factor to 0 and solving that equation. That will always work. So for this one and for the other one in there, -2x minus 3 equals 0. I'm just going to solve those little equations to figure out the x-intercept. So look, my x-intercept is +1. And my other x-intercept is -3/2. Why are these x-intercepts? Because that's what makes the y value 0. If I put 1, again, just watch. If I put 1 into that bracket, it's -1 plus 1, which is 0. 0 times that times that times that will be 0. Yes? If y is 0, my height is 0. I haven't gone up and I haven't gone down. That's an x-intercept. So when the bracket is 0, that's an x-intercept. And that's why you're doing this. Okay, so I said the x-intercepts were -3/2, 0, 1, and +1 and +5. -3/2 has an order of 3, 0 has an order of 1, 1 has an order of 2, it was squared, and 5 has an order of 1. Again, you add the orders together, you get the degree. We already know the degree, but 3 plus 2 is 5, plus 1 plus 1 is 7. So there you go. Cubic twist, pass through, turning, point, pass through. Now I can put it all together with the sketch. So I've got a cubic twist at -1.5, then a pass through at 0. So I have to turn to get that pass through. Then I have to turn again to get a turning point at 2. Then I have to pass through at 5. And look at how all of those match the end behavior. If I missed one of the x-intercepts, or if it was a turning point and I made it a pass-through, my end behavior would be wrong. All the properties of the graph will match. Like, I didn't force it to end down like that. I started up here because that's what we were supposed to do. But then I just did the cubic twist, the pass-through, the turning point, another pass-through, and I ended up down here. It has to match. And that's it.